This is part 2 of the lecture, and we continue with where we left off. We were looking at example 5.3 and we have just solved it. Now recall that we treated the problem as a non-homogeneous second order DE with two initial conditions, x naught at 0 equals to 2 and x prime at 0 equals to 0. So we use the usual method of solution and we obtain the solution x of t equals to, the first part is the xc, which is given by e to the negative 2t into 9 over 4 cos 2t plus 5 over 4 sin 2t. And we have the second part, which is the particular solution xp given by negative 1/4 cos 4t plus a half sin 4t. Now, in the example, the driving force f of t is a periodic function of the type f naught cos omega t. So the general solution for the non-homogeneous equation 10, where your b is bigger than 0, usually generally consists of a sum of a non-periodic function xct, which is the general solution of the homogeneous equivalent or the associated homogeneous DE, and a periodic part, which is the particular solution xp. We have also looked at the graph of the solution, and we can see that there is one portion of it which quickly dies down, right? This is the part that comes down, and then there's another part which sort of continues in an oscillatory manner. In fact, if we examine the solution carefully, we see that there is a portion, one part has a e to the negative 2t component, that is the negative exponential component, e to the negative 2t multiplied by some cosine and sine, and then it is the negative exponential that causes it to vanish, because as t tends to infinity, your e to the negative 2t will tend towards 0, so that only the periodic part will remain. Therefore, for large values of t, we find that only this part will be more dominant. In fact, because of this, we call the xct, that means xc, the part written in blue in this case, the transient term, because it disappears after a while. It comes and then it goes. And the other part, the xp, the particular solution part, we call it the steady state term, because it will remain there as time goes on. So we have the transient term and the steady state term. Now we look at another section called the undamped driven motion. In this case, we consider a spring mass system without damping. That means B is equals to 0. So here the support still moves under some kind of applied force, and the mass will move up and down as well. So the system may be modeled by the same equation as before, but with B equals to 0. So for example, we look at example 5.4. So in this case, we have a spring mass system that is driven by some oscillatory force, is 10 cos 4t, for example. So the initial conditions will be like as before. Since the mass is initially released from rest, we say that x prime at 0 is equals to 0 at a distance of 2 units from its equilibrium position. So at time t equals to 0, x is equals to 2. Think about this problem for a while. Now, we can work out this problem in the following manner. First of all, let's look at the diagram which describes this motion. Again, the support is moving up and down because of the driven force 10 cos 4t. Now we have one initial condition x prime at 0 equals to 0 and another one x at 0 equals to 2. We will keep that in mind. But first, to solve this problem, we look at the associated homogeneous DE, x double prime plus 8x equals to 0. So if we write down the auxiliary equation, it gives us m squared plus 8 equals to 0, and we can work out the solution or the roots of this auxiliary equation, namely m will be equals to plus or minus 2 root 2i. We can then write down the complementary function, which is also the general solution of the associated differential equation, xc equals to c1 cos 2 root 2t plus c2 sine 2 root 2t. For the particular solution, again we look at the right hand side. In this case, it's the same as before in the earlier example. The right hand side is 10 cos 4t. So for xp, we might try xp equals to a cos 4t plus b sine 4t. So we find the first derivative in order to find the second derivative with respect to t, and it's the second derivative that we will use to substitute into the equation. So substituting into the equation, we have this x double prime or 2x by dt square term, then plus 8 times x equals to the right hand side 10 cos 4t. Now it is not difficult to see in this case that we can work out the values of a and b, and in this case a is equals to negative 5 over 4 and b is equals to 0, and therefore we can write down our particular solution as negative 5 over 4 cos 4t. Now that we have found the particular solution, we can write down the general solution for this problem, which is x equals to c1 cos 2 root 2t plus c2 sine 2 root 2t minus 5 over 4 cos 4t. Now, to find the values of c1 and c2, we apply the initial conditions. X at 0 equals to 2 and x prime at 0 equals to 0. So we take the first derivative of x with respect to t, and then we can substitute t equals to 0 in both x and x prime, and we can work out the values of c1 and c2. In this case, we found that c1 is equals to 13 over 4 and c2 is 0. With these values, we can then write down the solution to the problem, which is x equals to 1/4 of 13 cos 2 root 2t minus 5 cos 4t. Now if we were to plot the graph of this solution, x equals to 1/4 times 13 cos 2 root 2t minus 5 times 4 cos 4t, we find that we get a picture like shown here, and you could see that there is some kind of a pattern that's being repeated. Now this is one portion, and it's sort of like being repeated here, here, and here. In fact, there's a name for these. These are called beats. So it is like the function being repeated. There is some kind of periodicity. In fact, if you look at the actual solution itself, it is clear that there is there's some kind of repetition of a pattern.